Okay, hello everyone. It's my great honor to be here to present our work, our bounded contrast learnable and approximately optimal. So this is joint work with Zhaohua, Chen, Xiaotie, Deng at Peking University and Zhiyi Huang at the University of Hong Kong. So in this talk, I will first introduce the formal model as well as the notation of contract design. Then the learnability problems of the finding optimal contracts in this paper, and finally our results. So actually, a typical example of hidden action model of the principal agent problem often happens between Xiaotie and me when he tries to incentivize me to conduct some, to organize some events for him. And he would always promise me that if the event turns out to be successful, he will just treat me to dinner. So the point here is that Xiaotie could not observe how much effort I have put in organizing the event, but he could only observe the outcome of the event and finally treat me according to the outcome. So in the formal model of contract design, a principal is responsible for a project which has n possible outcomes. Each outcome has a value between 0 and 1 to the principal. And the agent can take one of n possible actions, and an action A will lead to a probability distribution over the outcome space, the A, and the agent will bear a cost. So the principal could not induce a outcome by himself. So what he can do is actually to incentivize the agent to take an action that actually benefits the principal. So he does this by signing a contract P and by specifying a payment for each outcome. So under a specific payment contract P, the agents will take an action A star to maximize its utility, which is the expected payment minus the cost. And the principal's utility equals is the expected value minus the expected payment under the distribution induced by the agent's best responding action. So the time map of the contract design is as follows. First, the principal seeks the instance. Then the principal commits to a contract. The agent, based on the contract, will take a costly action that maximizes its own utility. The principal gets the value from the sample outcome and pays the agent according to the contract. So the computation of optimal contract actually reduced to solving nonlinear programming problems. So basically, we can treat the contract space as our strategy space, and we can partition the whole contract space into different polytopes, each corresponding to a agent action A. So if you, for example, if you choose to sign the contract that lies in the pink area, then we will know that the agent will take action A2. So the algorithm goes as follows. For each action, we just compute the cheapest contract to incentivize this action. And we just find the optimal one among all the solutions of all the solutions of the linear programming problems. So the observation here is that at the optimal contract, the agent, so the optimal contract is actually the solution of linear programming problems. So the agent is actually indifferent between the optimal action and some other action. So actually the contract is not that robust. So now here comes our learnability issue of finding optimal contracts. Recall that at the very beginning, the principal will seize the information of the instance, which not only includes the set of outcomes and the values, but also the agent's information, that is the set of actions, the cost of actions, and finally the outcome distributions. And those information can actually be the agent's private information, and we have no idea where to obtain them at the very first beginning. So here comes our question, that is, if I don't know the agent's information at all, can we efficiently learn the optimal contract through interaction with agents? We are trying to measure the efficiency through the sublinear regret or the poly query complexity. And we can study this problem through the online learning or banding model. So in this model, we can assume that the players play T rounds of the same contract design problem. And we assume that at the very beginning, the principal does not know the agent's information at all, but he indeed can see the set of outcomes and the corresponding values. So in each round T, the principal will choose a contract PT adaptively, and the agent will then take an action AT, which is the best response to PT, and is unobservable to the principal. And finally, outcome OT is sampled from DAT. That is observable to the principal. So our goal here is to try to minimize the regret, which is the optimal principal utility of cross runs minus the principal's total utility under the algorithm. And we want to achieve some sublinear regret, which basically means that on average, if the T tends to be infinite, we can actually tends to be optimal compared to the optimal principal utility. So in the literature, there have been mildly sublinear regret results for more and more general settings. Back to 2014, Holst, Livkins, and Vaughan focused on bounded and monotone contracts. Here, the bounded means that we always pay agents with a value that is between 0 and 1. And Cohen, Deligas, and Coren, they focus on bounded and smooth monotone contracts, but they allow the agents to be risk averse. And back last year, Zhao et al., they focus on general bounded contracts, and they provide an online learning algorithm which has a regret that is tight up to log factors. But actually, we can look into the regrets. This actually, that tends to be linear as the outcome space spans. What does it mean? It means that if I want to achieve some epsilon approximately optimal contract during the online learning models, actually I need to interact with the agent through an exponential number of times to achieve the epsilon approximately optimal. So is this good? Yeah, it is indeed good because it is sublinear regret, right? And it is tight, but it may not be good enough because we need exponential number of times to achieve epsilon optimal. So here comes our results. Well, we want to add some find this research gaps, answer those research questions, and get some and solving our curiosity. So the first question we are interested in is compared to the sublinear regret results. We are interested in, can we really get some truly sublinear regret algorithms under some mild assumptions? Here, the truly sublinear regret means that the regrets O tilde T of C for some epsilon constant C smaller than 1. And we provide a positive answer to the assumption under the assumption of first order stochastic dominance and concavity of distribution function property. As for the second question, one may notice that all the literature focuses on bounded contracts. So we are interested in whether the bounded contracts are approximately optimal to the general contracts. So with respect to this question, we give a negative answer with simply additive or multiplicative approximation, but we provide a positive answer for mixed approximation. And in this talk, I will mainly focus on the first result, which is the learning results. So what are the mild assumptions I just made? So first order stochastic dominance, it is actually a weaker assumption than the MLRP the former lecturer just talked about. So it basically means that for any actions A prime with CA no greater than CA prime, and for any outcome O star, the probability that an outcome is no worse than outcome O star under DA will be no greater than that under DA prime. This means that more efforts will yield better outcomes. And then the concavity of distribution function property means that for any outcomes A prime, and A prime prime, each having a cost greater than the former, and for any outcome O star. Okay, this is complex, but basically it means that the slope between the two actions with respect to the probability that an outcome is no worse than the O star is decreasing, and which means that agents' efforts have diminishing returns. And more importantly, we can actually find that all these two assumptions are talking about the relations between costs and the probability that some of the outcome is no worse than certain outcome. And we can actually treat this probability as a function of cost when fixing any arbitrary outcome. And we can actually get an alternative representation by distribution, this so-called distribution functions of the contract instances. And more importantly, FOSD and CDFP actually corresponds to the monotonicity and concavity of those distribution functions. So if we see the instance in this way, we can find out it really has some very good functional properties. Now we can make use of this to learn efficiently the information of those instances. So now here comes our algorithms. We are trying to learn the optimal contracts while learning the distribution functions of the instances. So it consists of two parts. In the first part, we consider a very simple action query model. So in this model, we assume that the principal knows there are finite number of actions, and the principal knows the cost of each action. And the principal will query an action A, and the agent will just return the outcome, which is sample from the distribution DA. And in this part, we want to, we can actually build estimated distributions EA that are sufficiently close to the true distributions, right? Just by querying the same actions enough times. And we want to design a epsilon optimal contract from the estimate distributions. And here, the technique is a robustification of the optimal contracts of the estimated distributions. And here comes our part two, which is the general contract query model. And we assume that the principal does not know the agent's information at all. And we even allow the agent has continuous space of actions. The principal can query a contract P at each round, and agent will return an outcome that is sampled from the distribution induced by the agent's best responding action. And here we want to design contracts to efficiently extract information about the distribution functions so that we can obtain sufficiently close estimates of BA. And then we can use the results in the first part and finally get our learning algorithms. And the technique here is to design an algorithm to learn convex functions through subgradient queries, and we're trying to realize the subgradient queries through the contract queries. So let me go into the details. First, the robustification in the first part. So why can't the estimate the distribution give the optimal contract of the estimate distribution be used directly to imply an epsilon optimal contract in the true distributions? The reason is that the solution of the linear programming problem is not continuous with respect to the perturbations. So the agent can actually take a totally different action that this make us suffering a loss. To overcome this, we construct a robustified contract P through P star by transferring an epsilon additional fraction of the principal's utility to the agent. So intuitively, we want to make agents' incentive more aligned with the principals, so as to incentivize actions that actually favor the leader. And the second part, how can we learn the distributions while threshold contracts? And interestingly, threshold contracts is exactly what the former talk speaker talked about, the quota bonus contracts. So basically, a threshold contract just will pay the agent P only if the outcome is at least as good as P star. So from the agent's perspective, it's trying to maximize the following value. and we let the derivative to equals to 0, and we can actually find out at the cost of the action the agents will choose. At that cost point, the function will have subgradient 1 over p. So now we just turn over the plane and we look into the inverse function. We'll find out at the corresponding probability point, the inverse function will have subgradient of p. And more importantly, if I just query the Deng contract enough times, we can actually get a good estimates of the probability points. So here is how our algorithm goes. We can just discrete the subgradients, and we make subgradient queries through threshold contract queries. And we can actually get the probability points corresponding to each subgradient. We then build up piecewise linear approximations of the estimated inverse functions using the line segments which has slope corresponding to the subgradients, and link them, and we can actually get very good estimates if the subgradient discretization is good enough. And then we can use the results in the first part to get our final results. That is an absolute optimal contract for the real instance. So in summary, we are interested in two questions with respect to the learning problem of optimal contracts. First, we want to find some mild assumptions under which we can get algorithms with polynomial query capacity of finding an optimal contract. Here we got a positive answer under the assumption of first order stochastic dominance and concavity of distribution function property. And second, we are interested in the approximate optimality of bounding contracts. We show that they are not approximately optimal with simply additive or multiplicative approximation, but they can indeed be approximately optimal for mixed approximation. So that's all for my presentation. If you are interested, feel free to scan to see our paper or just email any authors of us. And thank you for listening.